Hello and welcome. In this video, we'll be diving into a fundamental topic in algebra and calculus, the binomial theorem. By the end of this session, you will be able to expand binomials with positive integer powers, understand and apply the binomial theorem for rational powers, and use these expansions to solve a variety of problems, including finding specific terms and approximating values. We'll start with the basics of binomial expansions and build our way up to the more advanced concepts required for IBAAHL. Let's begin with the most intuitive way to understand binomial expansion. A binomial is simply an algebraic expression with two terms, like a plus b. So, a binomial is an expression with two terms, for example, a plus b. When we talk about a binomial expansion, we're referring to the result of raising a binomial to a power, like a plus b to the power of n. A binomial expansion is the result of raising a binomial to a power, such as a plus b to the power of n. You're likely already familiar with the simplest cases. For instance, a plus b squared. We know that a plus b squared expands to a squared plus 2ab plus b squared. But what about higher powers, like a plus b cubed? We can find this by multiplying a plus b by a plus b squared. So a plus b cubed is equal to a plus b times the expansion we just saw, a squared plus 2ab plus b squared. Now we distribute the terms. First we multiply a by each term in the second bracket. This gives us a cubed plus 2a squared b plus ab squared. Then we multiply b by each term. This adds a squared b plus 2ab squared plus b cubed. Finally, we collect the like terms. Combining the terms, we get our final expansion, a cubed plus 3a squared b plus 3ab squared plus b cubed. This process works, but it's clearly tedious for higher powers. Our goal is to find a more efficient method. Let's look closely at the expansions we found and see if we can spot a pattern. This is a key skill in mathematics. We have a plus b to the power of 0, which is 1. A plus b to the power of 1 is a plus b. A plus b squared is a squared plus 2ab plus b squared. And a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. First, let's examine the powers of a and b in each term. In the expansion of a plus b cubed, the powers of a are 3, 2, 1, and 0. They decrease by 1 in each subsequent term. Notice how the power of a starts at 3 and decreases to 0. Conversely, the powers of b start at 0 and increase to 3. The power of b starts at 0 and increases to 3. A crucial observation is that the sum of the powers in each term is always equal to the original power of the binomial. For a plus b cubed, 3 plus 0 equals 3, 2 plus 1 equals 3, and so on. The sum of the powers in each term is always 3. This pattern holds for any positive integer power, n. The powers of a decrease from n to 0, the powers of b increase from 0 to n, and the sum of the powers in each term is always n. Now let's focus on the coefficients. If we list them out for the expansions we've seen, we get a very interesting pattern. For a plus b to the power of 0, the coefficient is 1. For a plus b to the power of 1, the coefficients are 1 and 1. For a plus b squared, they are 1, 2, and 1. And for a plus b cubed, there are 1, 3, 3, and 1. This triangular arrangement of numbers is known as Pascal's triangle. It has a simple rule for its construction. Pascal's triangle is a triangular array of numbers where each number is the sum of the two numbers directly above it. Let's see how this works. The first row, corresponding to n equals 0, is just 1. The second row, for n equals 1, is 1, 1. The third row, for n equals 2, starts and ends with 1, and the middle term is 1 plus 1, which is 2. So, for n equals 2, we have 1, then 1, plus 1 is 2, then 1. For n equals 3, we start with 1. The next term is 1 plus 2, which is 3. The next is 2 plus 1, which is also 3. And we end with 1. For n equals 3, we have 1, then 1 plus 2 is 3, then 2 plus 1 is 3, then 1. We can continue this pattern to find the coefficients for any power. For example, for n equals 4, the coefficients would be 1, 4, 6, 4, 1. The coefficients for n equals 4 are 1, 4, 6, 4, 1. So the expansion of a plus b to the power of 4 is a to the 4th, plus 4a cubed b, plus 6a squared b squared, plus 4ab cubed, plus b to the 4th. This gives us the full expansion for a plus b to the power of 4. Let's put this knowledge into practice with a worked example. We'll expand 2x plus 3 cubed. Our goal is to expand 2x plus 3 cubed. First, we identify the power, n, which is 3. This tells us to use the third row of Pascal's triangle for our coefficients. The power is 3, so we use the coefficients from the third row of Pascal's triangle. 1, 3, 3, 1. Next, we identify our a and b terms. In this case, a is 2x and b is 3. We have a equals 2x and b equals 3. Now, we substitute these into the general expansion formula, being very careful with brackets. The expansion is 1 times 2x cubed plus 3 times 2x squared times 3 plus 3 times 2x times 3 squared plus 1 times 3 cubed. Let's simplify each term. The first term is 8x cubed. The first term is 8x cubed. The second term simplifies to 36x squared. The third term is 54x. And the last term is 27. So the full expansion is 8x cubed plus 36x squared plus 54x plus 27. A common mistake is to forget the brackets. For example, 2x squared is 4x squared, not 2x squared. Always use brackets to avoid errors. Pascal's triangle is great for small powers, but for larger powers, it becomes cumbersome. Imagine trying to find the 12th row. We need a more general formula. For higher powers, Pascal's triangle is too tedious. We need a general formula. Let's consider the expansion of a plus b to the power of n. This is a plus b multiplied by itself n times. The expansion of a plus b to the power of n is the product of n identical binomials. When we expand this, each term is formed by choosing either a or b from each of the n brackets and multiplying them together. For example, to get the term a to the power of n minus r times b to the power of r, we must choose b from r of the brackets and a from the remaining n minus r brackets. To get the term a to the power of n minus r times b to the power of r, we must choose b from r brackets and a from the other n minus r brackets. The number of ways to do this is the number of ways to choose r items from a set of n items, which is given by the binomial coefficient, n choose r. This number of ways is the binomial coefficient, n choose r, written as NCR, or with large parentheses. This coefficient is calculated using factorials. The formula for n choose r is n factorial divided by r factorial times n minus r factorial. This gives us the general term of the binomial expansion. The general term, or the r plus 1 th term, is t sub r plus 1 equals n choose r times a to the power of n minus r times b to the power of r. Notice that the index, r, starts at 0 for the first term, so the first term is t sub 1, which corresponds to r equals 0. The second term is t sub 2, which corresponds to r equals 1, and so on. Now we can state the full binomial theorem for positive integer powers. The binomial theorem states that for any positive integer n, the expansion of a plus b to the power of n is the sum from r equals 0 to n of n choose r times a to the power of n minus r times b to the power of r. Let's write out the first few terms of this sum to see how it works. When r is 0, we get n choose 0, a to the n, b to the 0. When r is 1, we get n choose 1, a to the n, minus 1, b to the 1. When r is 2, we get n choose 2, a to the n, minus 2, b to the 2, and so on, until r equals n, which gives us n choose n, a to the 0, b to the n. Remember that n choose 0 and n choose n are both equal to 1. This confirms that the first and last terms of the expansion always have a coefficient of 1. Since n choose 0 and n choose n are both 1, the expansion starts with a to the n and ends with b to the n. This theorem provides a powerful and systematic way to expand any binomial to a positive integer power. Let's use the binomial theorem to find a specific term in an expansion without having to write out the whole thing. This is a very common type of IB question. Our objective is to find the seventh term of the expansion of 3x minus 4 over x squared to the power of 14. First, we identify our key values. The power n is 14. The first term, a, is 3x, and the second term, b, is negative 4 over x squared. We have n equals 14, a equals 3x, and b equals negative 4 over x squared. We are looking for the seventh term. Remember that the general term formula is t sub r plus 1. So if we want the seventh term, r plus 1 must equal 7, which means r must be 6. For the seventh term, r plus 1 equals 7, so r equals 6. Now we substitute these values into the general term formula. T sub r plus 1 equals n choose r, a to the n minus r, b to the r. The seventh term is 14 choose 6 times 3x to the power of 14 minus 6 times negative 4 over x squared to the power of 6. Let's simplify the powers. 14 minus 6 is 8. This becomes 14 choose 6 times 3x to the 8th times negative 4 over x squared to the 6th. The question asks us not to simplify the answer, so we can leave it in this form. This is the seventh term of the expansion. Another common problem is finding the coefficient of a specific power of x, or finding the constant term. Let's work through an example. We need to find the coefficient of x to the power of 6 and the constant term in the expansion of x squared plus 4 over x to the power of 12. First, we write down the general term, t sub r plus 1. Here, n is 12, a is x squared, and b is 4 over x. So the general term is 12 choose r times x squared to the power of 12 minus r times 4 over x to the power of r. Now, we need to simplify this term, especially the powers of x. Using the rules of exponents, x squared to the power of 12 minus r is x to the power of 24 minus 2r. And 4 over x to the power of r is 4 to the r over x to the r. This simplifies to 12 choose r times 4 to the r times x to the power of 24 minus 2r divided by x to the r. Combining the x terms, we subtract the powers. The general term is 12 choose r times 4 to the r times x to the power of 24 minus 3r. This is our simplified general term. Now we can answer the questions. For part A, we want the coefficient of x to the power of 6. We set the power of x in our general term equal to 6. Solving for r, we get 3r equals 18, so r equals 6. This means the term we're looking for is the seventh term. So r equals 6. The coefficient is everything in the general term except the x part. The coefficient is 12 choose 6 times 4 to the power of 6. Calculating this gives us 3, 784, 704. For part B, we want the constant term. A constant term is one where the power of x is 0. So we set the power of x in our general term to 0. Solving for r, we get 3r equals 24, so r equals 8. This is the ninth term, so r equals 8. The constant term is the coefficient of this term. The constant term is 12 choose 8 times 4 to the power of 8. This calculates to 32, 440, 320. So far, we've dealt with positive integer powers. But what if the power is a fraction or a negative number? This is where the binomial theorem for rational powers comes in. Sir Isaac Newton generalized the binomial theorem to include any rational power, n, not just positive integers. The formula looks very similar, but there's a crucial difference. For rational powers, the expansion is an infinite series. The expansion of 1 plus x to the power of n is an infinite series. The coefficients are calculated using a generalized binomial coefficient. The generalized binomial coefficient, n choose r, is defined as n times n1 times nr plus 1, all divided by r factorial. This formula works for any rational n. If n happens to be a positive integer, the series terminates because one of the factors in the numerator will eventually become 0. Because this is an infinite series, it doesn't always converge to a finite value. It only converges for certain values of x. The expansion of 1 plus x to the power of n is only valid, or converges, when the absolute value of x is less than 1. This means x must be between -1 and 1. This condition is extremely important and must always be stated when using this theorem. Let's apply this to a more complex expression. We'll expand a plus bx to the power of n. Our goal is to expand a plus bx to the power of n, where n is a rational number. The key is to manipulate the expression to fit the 1 plus x to the n form. We can do this by factoring out a. We factor out a from the bracket, which gives us a to the n times 1 plus bx over a to the power of n. Now, we can expand the 1 plus bx for a to the n part using our formula. Let's call the term bx for a our new x. The expansion is a to the n times the series 1 plus n times bx of a plus n and 1 over 2 factorial times bx of a squared, and so on. The interval of convergence is determined by the new x term. The absolute value of bx slash a must be less than 1. The condition for convergence is that the absolute value of bx over a is less than 1. This can be rearranged to find the range of x values. This means x must be between the negative absolute value of a over b and the positive absolute value of a over b. This is the general method for expanding binomials with rational powers. Always remember to factor out the first term and state the interval of convergence. Let's work through a full example. We'll expand 1 over the square root of 2 plus x. We need to expand 1 over the square root of 2 plus x up to the term in x cubed and state the interval of convergence. First, we rewrite the expression in the form a plus bx to the n. 1 over the square root of 2 plus x is the same as 2 plus x to the power of -1/2. Now, we factor out the first term, 2. This becomes 2 to the power of -1/2 times 1 plus x over 2 to the power of -1/2. 2 to the power of -1/2 is 1 over the square root of 2. So our expression is 1 over root 2 times 1 plus x over 2 to the power of -1/2. This is 1 over root 2 times 1 plus x over 2 to the power of -1/2. Now we expand the bracket. Here, n is -1/2, and our po(x) term is x over 2. The expansion is 1 plus n times x plus nn1 over 2 factorial times x squared plus nn1 n2 over 3 factorial times x cubed, and so on. Let's simplify each term inside the bracket. The first term is 1. The second is -x over 4. The third is 3x squared over 32. And the fourth is -5x cubed over 128. Now, let's find the interval of convergence. The condition is that the absolute value of our x term x over 2 must be less than 1. The condition is the absolute value of x over 2 is less than 1. This means x must be between negative 2 and 2. So the expansion is valid for x between negative 2 and 2. A powerful application of these infinite series expansions is to approximate values. Let's use our previous expansion to estimate 1 over the square root of 2.1. We will use our expansion of 1 over the square root of 2 plus x to estimate 1 over the square root of 2.1. We need to find the value of x that makes 2 plus x equal to 2.1. Clearly, x must be 0.1. We set 2 plus x equals 2.1, which gives us x equals 0.1. First, we must check if this value of x is within our interval of convergence. Our interval was minus 2 less than x less than 2. Since 0.1 is within this range, the approximation will be valid. Since 0.1 is between negative 2 and 2, the approximation is valid. Now we substitute x equals 0.1 into our expansion. We substitute 0.1 for x in our expansion. Let's calculate the value inside the bracket. This simplifies to 1 minus 0.025 plus 0.000937 minus 0.00000390625. Adding these up gives us approximately 0.9758984,375. The sum inside the bracket is approximately 0.9758984,375. Finally, we multiply by 1 over the square root of 2, which is approximately 0.70710678. Multiplying by 1 over root 2 gives us our approximation of 0.690064. Using a calculator, the actual value of 1 over the square root of 2.1 is approximately 0.690066. Our approximation is very close, demonstrating the power of this method. Let's tackle a more advanced problem that combines several concepts. We need to find the coefficient of x squared in the expansion of a product of two binomials. We need to find the coefficient of x squared in the expansion of 1 minus 3x cubed times 1 plus 2x to the power of negative 2. First, we rewrite the expression to make it easier to work with. This is the same as 1 minus 3x cubed times 1 plus 2x to the power of negative 2. We need to expand each part separately, but we only need to go up to the x squared term, as anything higher will not contribute to the coefficient of x squared in the final product. We will expand each part up to the x squared term. For the first part, 1 3x cubed, we can use Pascal's triangle or the binomial theorem. The expansion is 1 cubed plus 3 times 1 squared times minus 3x plus 3 times 1 times minus 3x squared plus higher order terms. For the second part, 1 plus 2x to the power of negative 2, we use the rational power formula. The expansion is 1 plus n times x plus nmn1 over 2 factorial times x squared plus higher order terms. Now we multiply these two expansions together. But we only care about the terms that result in x squared. We are multiplying 1 minus 9x plus 27x squared by 1 minus 4x plus 12x squared. There are three ways to get an x squared term. First, the constant term from the first bracket times the x squared term from the second. This gives us 1 times 12x squared, which is 12x squared. Second, the x term from the first bracket times the x term from the second. This gives us minus 9x times minus 4x, which is 36x squared. Third, the x squared term from the first bracket times the constant term from the second. This gives us 27x squared times 1, which is 27x squared. Now we add the coefficients of these x squared terms. The total coefficient is 12 plus 36 plus 27, which equals 75. So the coefficient of x squared in the expansion is 75. Let's look at one more type of problem, finding unknown constants. This often involves comparing coefficients. We are given that the expansion of 1 plus kx to the power of n starts with 1 minus 12x plus 60x squared. We need to find the values of k and n. First, we write out the expansion of 1 plus kx to the power of n using the rational power formula. The expansion is 1 plus n times kx plus nn1 over 2 factorial times kx squared plus higher order terms. Now we group the terms by powers of x. This gives us 1 plus nkx plus nn1 k squared over 2 x squared and so on. We are told that this expansion is equal to 1 minus 12x plus 60x squared. By comparing the coefficients of the x terms, we can form equations. Comparing the coefficients of x, we get our first equation. nk equals negative 12. Comparing the coefficients of x squared, we get our second equation. nn1k squared over 2 equals 60. We now have a system of two equations with two unknowns. From equation 1, we can express k in terms of n. From the first equation, k equals negative 12 over n. Now we substitute this into equation 2. Substituting k into the second equation gives us nn1 times negative 12 over n squared, all divided by 2, equals 60. Let's simplify this. Minus 12 slash n squared is 144 over n squared. This simplifies to nn1 times 144 over n squared, divided by 2, equals 60. We can cancel an n from the numerator and denominator and divide 144 by 2. This leaves us with 72 times n1 over n equals 60. Now we solve for n. Multiply both sides by n. We get 72n minus 72 equals 60n. Rearranging gives 12n equals 72, so n equals 6. Solving for n, we find that n equals 6. Finally, we substitute n equals 6 back into our expression for k. K equals negative 12 over 6, which is negative 2. So, we have found our unknown constants, n equals 6 and k equals negative 2. Now it's your turn to practice. Here are 5 IB-style questions for you to try. Pause the video and work through them. Here are 5 practice questions. Take your time to solve them. Welcome back. Let's go through the solutions together. Here is the solution to the first question. Question 1 asks for the coefficient of x cubed in the expansion of 2x3 to the power of 5. We use the general term formula, t sub r plus 1 equals n choose r, a to the n, minus r, b to the r. Here, n is 5, a is 2x, and b is minus 3. The general term is 5 choose r times 2x to the 5 minus r power times minus 3 to the r power. We want the term with x cubed, so we set the power of x, which is 5 minus r, equal to 3. This gives r equals 2. Setting 5 minus r equals 3 gives r equals 2. Now we substitute r equals 2 into the general term. The term is 5 choose 2 times 2x cubed times minus 3 squared. 5 choose 2 is 10. 2x cubed is 8x cubed. And minus 3 squared is 9. This simplifies to 10 times 8x cubed times 9. Multiplying these together, we get 720x cubed. The coefficient is 720. Here is the solution to the second question. Question 2 asks for the constant term in the expansion of x squared plus 1 over x to the power of 9. Again, we start with the general term. Here, n is 9, a is x squared, and b is 1 over x. The general term is n choose r times a to the power of n minus r times b to the power of kakatif r. We simplify the powers of x. This gives x to the power of 18 minus 2r divided by x to the r. The x term simplified to x to the power of 18 minus 3r. For a constant term, the power of x must be 0. So we set 18 minus 3r equal to 0. Solving for r, we get 3r equals 18, so r equals 6. The constant term is the coefficient when r is 6. The constant term is 9 choose 6. 9 choose 6 is the same as 9 choose 3, which is 9 times 8 times 7, divided by 3 times 2 times 1. This equals 84. The constant term is 84. Here is the solution to the third question. Question 3 asks us to expand 1 minus 2x to the power of negative 1 up to the x cubed term, and state the interval of convergence. We use the rational power formula here. N is minus 1, and our Kotzke x term is minus 2x. The expansion is 1 plus n times x plus nmn1 over 2 factorial times x squared plus nm1 n2 over 3 factorial times x cubed. Let's simplify each term. The first term is 1. The second is 2x. The third is 4x squared. And the fourth is 8x cubed. Now for the interval of convergence. The absolute value of our x term, minus 2x, must be less than 1. The condition is the absolute value of minus 2x is less than 1. This is the same as the absolute value of 2x being less than 1, which means x must be between negative 1/2 and 1/2. The expansion is valid for x between negative 1/2 and 1/2. Here is the solution to the fourth question. Question 4 asks for the coefficient of x squared in the expansion of 1 plus x times 1 minus 3x to the power of negative 2. We expand the second part, 1 3x, to the power of negative 2 up to the x squared term. The expansion is 1 plus n times x plus nn1 over 2 factorial times x squared. Now we multiply this by 1 plus x. We are multiplying 1 plus x by 1 plus 6x plus 27x squared. We look for terms that give x squared. First, 1 times 27x squared. This gives 27x squared. Second, x times 6x. This gives 6x squared. Adding the coefficients, 27 plus 6 equals 33. The coefficient of x squared is 33. The coefficient of x squared is 33. Here is the solution to the fifth and final question. Question 5 states that the expansion of 1 plus ax to the power of n is 1 plus 12x plus 60x squared. We need to find a and n. We expand the left side using the rational power formula. The expansion is 1 plus n times ax plus nn1 over 2 factorial times ax squared. Comparing coefficients with the given expansion, we get two equations. Comparing the x terms gives na equals 12. Comparing the x squared terms gives nn1 a squared over 2 equals 60. From equation 1, a equals 12 over n. We substitute this into equation 2. This gives nn1 times 12 over n squared divided by 2 equals 60. Simplifying, we get 72 n1 over n equals 60. This simplifies to 72 n1 over n equals 60. Solving for n, we find n equals 6. Solving this equation gives n equals 6. Substituting n equals 6 back into equation 1, we get 6a equals 12, so a equals 2. Substituting n equals 6 into the first equation gives a equals 2. So the values are a equals 2 and n equals 6. Let's quickly recap what we've covered. We started with binomial expansions for positive integer powers, using Pascal's triangle to find coefficients. We began with positive integer powers, using Pascal's triangle for coefficients. We then introduced the binomial theorem, which provides a general formula for any term in an expansion using binomial coefficients. We learned the binomial theorem, which uses binomial coefficients for a general term. Finally, we extended this to rational powers, which results in an infinite series that converges only for a specific interval of x values. We extended the theorem to rational powers, resulting in an infinite series with a specific interval of convergence. We've seen how to use these tools to find specific terms, coefficients, and even to approximate values. Mastering these techniques is essential for success in IB-DAY-AHL. Thank you for watching. Keep practicing, and you'll become proficient in the binomial theorem.